In this video, we're going to go back and have a look at a concept called stationary points with the intention of building a bit more of an understanding around, firstly, what they are, and then secondly, why they're so important. So jumping into it, the first question we're going to ask ourselves is, we'll go back to basics and say, what does a derivative tell us? And a simple definition of derivative could be, well, for a function f of x, its derivative f dash of x will tell us the slope of the function f of x. Alright, cool. So next question is, well, okay, if we know what a derivative is, then let's go one little step further and say, well, what's a stationary point? Now, to answer that question, let's have a look over on the right here. What I've done is I've got a function, but we don't actually have its definition. Rather, we only have what it looks like on a graph. Now, imagine if I said, let's find the derivative of this function simply by looking at it. And what we'd do is we'd look at the point at where the function stands still, so here and here, and we'd mark it on the x-axis like so. Then we'd have a look on each little section. What we can see in the far left, the function as x increases, y increases, so we say it's a positive slope. After this point here, we'd say as x increases, y decreases, and then finally as x increases, y also increases. Now, the points at which the graph changes over from increasing to decreasing, we call this point here a stationary point. Stationary point. And of course there's one here as well. So stationary points tell us when the slope of a graph is equal to 0. Now, this isn't always the only condition when we see stationary points. So what we can see is that, so say for example, over here, the graph that's transitioned from being positive slope to negative slope, sometimes you'll see a stationary point where it transitions from positive and then it sort of stands still and then it goes back positive again. So the important thing to remember is that the stationary point itself is simply where we see the slope of a graph just stop momentarily, so equals 0 for a little bit. Now the next question is, well, if we know how to find them, then, if we know what they are, then the question is, how do we find them on a graph? And let's consider if we go down and we take if we just take the derivative of this function here, what we'd find is that using our knowledge, we're going to see positive slope here, negative slope here, and positive slope here. So what we see is that to be able to find a stationary point, we simply have to take the derivative of the function and look for when the derivative equals 0. So how do we find stationary points? Well, it's simply a case of look for when the derivative equals 0. Alright, so if we go down a little, what we've got is we've got this purple function still over here. This purple function here, and we've been given its definition, and by definition f of x is defined as x cubed minus 8x squared plus 17x minus 10. And subsequently, using the simple power rule, what you'd find is that the derivative of the purple function f of x, this green function f dash of x, is defined as 3x squared minus 16x plus 17. Now, if we have a question where it says find the stationary points of f of x, then we can do this in 3 steps. So remember, the stationary points are the locations, or the stationary points of this purple graph, f of x, are the locations at where the derivative itself cuts the x-axis, or the roots of the derivative function. So to find the locations of the stationary points, so say here, and say down here, then what we're going to find is we need to find when find the derivative of f of x, then find the roots of f dash of x, and then finally, when we find the roots of f dash of x, substitute the roots into f of x. Alright, so finding this process, what we already know is, well, f dash of x is defined as 3x squared minus 16x plus 17. So that's given to us. Now for part 2, we have to set f dash of x to 0. So if we've got 3x squared like so minus 16x plus 17, then what we're looking for is don't care about f dash of x, we're going for when does f dash of x equal 0. Now, to make, firstly, what we have here is we've got an equation where 0 equals 3x squared minus 16x plus 17. So effectively what we've got is a quadratic. And the way in which we solve quadratic functions is we have to factorize and then use null factor law. So look at what we have to make x to make it equal 0. Now, observing this particular function here, what you can see is firstly it's non-monic. So let's get rid of the non-monic behavior simply by dividing everything through by 3. So 0 will equal x squared minus 16 over 3 x plus 17 over 3. Awesome. And now, observing this function here, we can deduce two things. So firstly, because we're already given a graph and we can see that the function itself does indeed cut the x-axis, we know that we're expecting to see some real solutions or some real roots. But notice that over on the function itself, looking at the value of c, so the constant in the equation, it's 17 over 3, and simply looking at that, the number itself, it's already an irrational number. So what we're going to expect is that this function here, or this quadratic here, it's not going to be solvable simply by inspection, but rather we're going to see the solutions to x here are going to be real but irrational. So what we need to do is we need to solve the values of x using the quadratic formula. So in this case, we're going to go Alright, cool. Now plugging this into the calculator, instantly we find that we get two real distinct solutions, none of which are rational, but the first one we find is x equals 1.465, and the second one is 3.869. So of course we're getting two real but non-rational solutions. So instantly what we can see is that we can go this one up here, that's a 1.465, and this one down here, this is 3.869. Alright, so we've got the locations of x, but now we need to know the locations of y. And from previous experience, what you may realize is that, well, if you've got the location of x here, then it's simply a matter of going, well, what is f of 1.465, like so. So it's simply a case of, well, we need to substitute this value of x here back into the original function and calculate that value there. So simply all we have to do to get the y value is, this is in step 3 by the way, is f of 1.465 equals, and f of 3.869. And in this case, you could either use your calculator and simply plug in the value of x into your calculator using this guy here, or using this equation here, or you could simply graph it and then use your xcalc or ycalc to solve the values here. In this case, I've already pre-configured, or I've already solved it on my calculator, so I'll just write the solutions down there. So the first solution is 0.879, and the second solution is negative 6.065. Like so. So the points themselves, the point over here, this one is 0.8779, and this one here is negative 6.065. So going back in summary, a stationary point is simply a position on a graph where the slope itself sits at 0. To find them, all we need to do is you take the derivative of the function that you're looking for the stationary points of. You then solve the roots of that derivative function, and the x location of those roots, you plug that back into the original function, and that will tell you the location, the y location of the stationary points. So it's as simple as that for doing stationary points to begin with. Now it does get a little bit more complicated after this, but we'll take it one step at a time, and if you can calculate the stationary points on a simple function like this, then we'll call it success for now.